Welcome to our focused session on the JavaScript math object. In programming, you will constantly face scenarios where simple addition and subtraction are not enough. You might need to round a user's purchase total, calculate the distance between two geographical points, or generate a random number for a game mechanic. This is where the math object becomes your indispensable toolkit. Unlike other objects you might instantiate, math is a static library, meaning you never create a new math variable, you simply access its powerful methods directly. We will explore 12 essential functions that cover everything from basic rounding strategies, knowing when to floor, ceiling, or truncate, to more complex arithmetic like exponents and square roots. We will also discuss the limitations of this library when working with the newer big int type. By the end of this module, you will have the confidence to handle any numerical challenge the language throws at you. Let's begin with the most fundamental operation, standard rounding. The math.round function behaves exactly as you were taught in elementary school mathematics. It looks at the fractional part of a number to decide its fate. If that fraction is 0.5 or greater, the number is pushed up to the next integer. If it is anything less than 0.5, it snaps down to the lower integer. This symmetry is intuitive for positive numbers, but you must be careful with negative values, where up technically means closer to 0 in magnitude. For instance, negative 1.5 rounds to negative 1, while negative 1.6 would round to negative 2. This method is your go-to for general-purpose rounding when you need to smooth out rough data, display cleaner prices, or simplify statistics for a user interface, ensuring the value remains as close to the original truth as possible. Now, consider a scenario where you need absolute certainty that a number will never exceed its current integer value. This is the domain of math.floor. As the name suggests, this function forces the number down to the floor, effectively returning the largest integer that is less than or equal to your input. For positive numbers, this looks like simply chopping off the decimal. 4.9 becomes 4. However, the behavior with negative numbers is where many developers trip up. Because floor means moving left on the number line towards smaller values, negative 4.1 does not become negative 4. It moves down to negative 5. You will frequently use this method when calculating array indices, converting time loops, or anywhere you need to ensure a value stays within a lower bound. It is a tool of strict reduction, guaranteeing the result is never larger than the source. The opposite counterpart to the floor function is math.ceil, short for ceiling. This method adopts an optimistic approach, always rounding the number up to the smallest integer greater than or equal to the input. Even if the fractional part is a tiny non-zero amount like 0.001, math.ceil will elevate the entire number to the next step. For example, 4.1 becomes 5. This logic is crucial for calculations like pagination. If you have 41 items and display 10 per page, you need 5 pages, not 4. Division alone would give you 4.1, and rounding down would leave one item hidden. Just like with floor, pay attention to negatives. Since up on the number line is towards positive infinity, negative 4.9 moves up to negative 4. Use this whenever you need to ensure a container is large enough to hold a fractional quantity. Sometimes you do not care about rounding logic, direction, or the number line. You simply want to discard the chaos of the decimal and keep the clean integer. Math.trunc is the tool for this specific job. It performs a pure truncation, surgically removing any fractional digits without any mathematical rounding. For positive numbers, it acts identically to the floor function. However, its distinct personality shines with negative numbers. While floor pushes negative 4.9 down to negative 5, trunc simply deletes the 0.9, leaving you with negative 4. This behavior makes it behave like a round towards zero function. It is particularly useful when parsing raw data streams where the decimal represents noise rather than value, or when you are implementing algorithms that require integer-only arithmetic regardless of the sign. In many algorithms, the direction of a value, whether it is positive or negative, is irrelevant compared to its magnitude. Math.abs calculates the absolute value, stripping away the sign to return a strictly non-negative result. If you pass it -5, you get 5. Pass it +5, and it remains 5. This simple function is mathematically profound and essential for calculating the difference or distance between two numbers without worrying about which one is larger. For instance, to find the gap between a user's score and a high score, you subtract them and apply absolute value, ensuring the result is always a positive distance. It is also the first step in collision detection algorithms in games, where you check overlap based on distance rather than coordinates. It effectively tells you how much without caring about which way. Finding the largest number in a dataset is a common requirement, and math.max simplifies this into a single function call. You can pass it any number of arguments and it will instantly return the highest value among them. It is incredibly efficient for comparing scores, determining boundaries, or finding the latest timestamp. A powerful pattern in modern JavaScript involves using this method with the spread syntax. If you have an array of thousands of numbers, you cannot pass the array directly, but by spreading it, math.max can process the entire list at once. Be aware, however, that if any argument you pass is not a number and cannot be converted into one, the result will be nan, breaking your calculation. This function is your primary tool for establishing upper limits and filtering for the best performing metrics in your data. Directly opposing the max function is math.min, which scans its arguments to return the lowest value. While its usage for finding the smallest number is obvious, its most sophisticated application is in clamping logic. Imagine you have a user input field that should not exceed 100. You can pass the user's input and the number 100 into math.min. If the user enters 50, the function returns 50. But if they enter 500, the function returns 100, effectively capping the value at your desired maximum. This technique is ubiquitous in game development for health bars, in UI design for limiting scroll positions, and in financial software to prevent overdrafts. It allows you to enforce safety limits elegantly without writing verbose if-else statements to check boundaries. When you need to raise a number to a specific power, math.pow is the classic method to employ. It takes two arguments, the base and the exponent. So passing 2 and 3 calculates 2 to the power of 3, resulting in 8. While this function has been a staple of JavaScript since the beginning, it is worth noting that modern syntax introduced the double asterisk operator, which performs the same task with a cleaner, more mathematical look. However, math.pow remains relevant for dynamic calculations, where compatibility with older code bases is necessary. You will use this extensively in formulas for compound interest, physics simulations involving acceleration, or any geometric scaling algorithm. It handles negative exponents as well, allowing you to easily calculate fractions and inverse squares without manual division logic. The inverse of squaring a number is finding its square root, and math.sqrt performs this calculation efficiently. If you pass it 9, it returns 3. This function is a cornerstone of geometry and trigonometry, essential for calculating diagonals, distances, and areas. However, it strictly adheres to real number mathematics, meaning if you pass it a negative number, it will return nan instead of an imaginary number. This not a number result is a signal that your input data might be invalid or corrupted. You will often find math.sqrt paired with math.pow when implementing the Pythagorean theorem manually. Whether you are resizing images while maintaining aspect ratio or calculating the standard deviation in a statistical analysis app, this function is the engine driving those dimensional transformations. Perhaps the most frequently discussed method is math.random, the source of all unpredictability in your scripts. It returns a pseudo-random floating point number that is greater than or equal to 0, but strictly less than 1. This means you will never get a pure 1 from this function. While a decimal, like 0.4, might seem useless on its own, it is the seed from which all other random ranges grow. To get a random integer between 1 and 10, you multiply this result by 10, floor it, and add 1. Mastering this transformation formula is a rite of passage for developers. You will use it to shuffle decks of cards, spawn enemies at random locations, decide probability outcomes in A/B testing, or generate temporary unique IDs for session data. A relatively newer addition to the language, math.sign provides a specialized utility to determine the nature of a number without caring about its value. It returns 1 if the number is positive, -1 if it is negative, and 0 if the number is 0. This simplifies conditional logic significantly. Instead of writing complex checks to see if a value is greater than or less than 0, you can simply check the sign. This is particularly useful in physics engines to determine the direction of velocity, in financial apps to color code gains versus losses, or in sorting algorithms to determine relative order. It also handles string coercion, so passing the string -5 will correctly return -1, adding a layer of robustness to your input processing. For years, developers calculated the hypotenuse of a triangle by squaring two numbers, adding them, and then taking the square root. Math.hype replaces that entire boilerplate with a single optimized function. You simply pass the lengths of the sides, and it returns the square root of the sum of their squares. Beyond just convenience, it handles multiple arguments, allowing you to calculate the magnitude of vectors in 3D or even n-dimensional space effortlessly. It is also safer than the manual method because it avoids intermediate overflow errors that can happen if you square very large numbers before rooting them. This method is invaluable for graphics programming, data visualization, and anywhere Euclidean distance is the key metric. Before we conclude, we must address a critical limitation. The math object was designed in an era before BigInt existed, and as such, it is strictly incompatible with this new type. Math methods expect standard floating point numbers. If you attempt to pass a BigInt, a value suffixed with n, into functions like math.sqrt or math.round, JavaScript will throw a type error and crash your script. This is a hard constraint. If you absolutely must use these functions on a BigInt, you are forced to manually convert it to a standard number first. However, be warned, doing so defeats the purpose of BigInt, as you will immediately lose the precision that BigInt was meant to preserve. Always keep your large integer logic separate from standard math library operations. We have successfully navigated the extensive capabilities of the JavaScript math object. We started with the nuances of rounding using round, floor, ceil, and trunc, giving you total control over integer conversion. We examined utilities for analyzing numbers like absolute value and sign, and calculation tools for limits with min and max. We delved into power functions with exponents and square roots, explored the generation of randomness, and simplified geometry with the hypotenuse function. Finally, we highlighted the critical incompatibility with BigInt. This static library is a fundamental pillar of the language. Whether you are building games, data dashboards, or financial tools, these 12 methods will be constants in your daily development work, empowering you to solve complex numerical problems with clean, native code.